Advanced reasoning models like OpenAI's O3 and DeepSeek R1 routinely achieve 90% accuracy on high-level mathematical benchmarks, like the AIME test. Yet, when researchers place a 3D printed turtle covered in a subtle adversarial noise pattern in front of these same systems, the performance often collapses. Despite its obvious physical form, the system examines the object and classifies it as a rifle, locking in the error with 99% confidence. Research from Goldsmiths, University of London, suggests that this represents a core architectural limitation. Modern AI operates by mapping inputs to labels through millions of weighted connections. This statistical approach excels at interpolation, but it lacks the internal mental models required to reason through scenarios that fall outside its specific training distribution. Human intelligence relies on grasping the causal mechanisms of how the world works. In contrast, neural networks find statistical correlations. They map out familiar patterns they have seen before and estimate the spaces between them, leaving them vulnerable when presented with genuinely novel information. The precision paradox occurs when a model provides a definitively wrong answer with extreme certainty. The model achieves this state by overfitting, memorizing the specifics of its training set rather than deriving a generalized rule that applies to the real world. We see the consequences of this overfitting in fraud detection. An algorithm can process millions of transactions to catch known anomalies, but it may completely ignore a novel fraud tactic because the new method does not match its memorized historical patterns. These systems simulate comprehension through high-speed pattern matching. This makes their current architecture an unreliable foundation for autonomous moral or critical decision-making. To identify why these errors occur, we must look at how language models process human concepts. This is an embedding space. Concepts map as geometric coordinates within a high-dimensional space, clustering together based on training data. By calculating spatial distances, taking the vector for king, subtracting man, and adding woman, the resulting coordinate lands near queen. The model completes the analogy based on vector coordinates. It relies on the geometric proximity of tokens, without possessing a semantic comprehension of what a human monarch actually is. Philosopher John Searle illustrated this mechanism with the Chinese room thought experiment. An operator inside a room receives a message in Chinese, consults a vast rulebook to find the corresponding characters, and sends a reply out. The operator produces a flawless response while following a rulebook, without actually learning the language. Genuine artificial general intelligence requires moving beyond these pure correlation engines toward architectures that can build internal representations of meaning. Transitioning to reliable artificial general intelligence requires implementing the specific functional mechanisms that allow biological brains to deliberate before they act. Cognitive scientists model this deliberation through global workspace theory, a neuropsychological framework detailing how functional consciousness operates in the brain. The theory posits that the nervous system runs multiple specialized subconscious processes in parallel. These disjointed processes analyze incoming data and compete to enter a central global workspace, which prioritizes what deserves immediate attention. This creates a continuous action-perception cycle. The mind samples sensory inputs, makes sense of the situation, and selects an appropriate physical or cognitive action in response. Translating global workspace theory into software allows researchers to build artificial moral agents that can evaluate choices rather than just predicting tokens. This approach focuses on engineering an architecture capable of taking fragmented data and synthesizing it into a cohesive, deliberative understanding of the environment. This is the LIDA cognitive cycle, a software implementation of global workspace theory. The LIDA model operates in discrete loops, processing a unit of sensing, attending, and acting roughly every 300 milliseconds. The loop begins with sensory stimuli. Low-level feature detectors evaluate incoming data from external and internal sources. Specialized processors, called structure-building codelets, draw on perceptual memory to assemble these raw features into recognizable pre-conscious concepts, such as objects or relations. Data enters the workspace. The system integrates new percepts with recent models to assemble a transient internal representation of its current situation. Portions of this model compete for attention. Attention codelets form coalitions, fighting to bring specific structures to the forefront. The winning coalition triggers the conscious broadcast. This data is distributed globally across all systems, forcing the agent to prioritize this specific information when selecting its next action. Finally, procedural memory receives the broadcast and identifies templates of possible actions. The action selection mechanism chooses a single response, which is then executed by the sensory motor memory. This cycle ensures that the system's actions are driven by a synthesized, attended model of reality, creating a structure for more reliable autonomous behavior. Integrating ethics into LIDA requires applying constraints directly into this 300-millisecond cognitive loop. Moral filtering begins at the subconscious level. Bottom-up values and affective responses act as filters while the system assembles the situational model in the workspace. Top-down deliberative rules, like utilitarian logic or specific duties, act as heavy constraints during the conscious broadcast phase. This allows the system to check a proposed action against programmed ethical principles before execution. Moral decision-making in LIDA functions as a hybrid emergent property. It relies on the same core mechanisms as general decision-making, integrating values and principles into every cognitive cycle. True artificial moral agents emerge when ethical boundaries are generated by this continuous fusion of subconscious reflex and conscious reflection. Deploying autonomous reasoning AGI at scale alters the way nations produce value and maintain geopolitical relevance. Automation extends to both mechanical tasks and complex cognitive labor. When machines handle strategy, logistics, and production autonomously, human survival is decoupled from traditional employment. This shift disrupts the economic concept of comparative advantage, the principle that nations benefit from specializing based on differences in opportunity costs. Historically, many developing nations relied on low-cost human labor to maintain an advantage in manufacturing. AGI alters this. Developed nations with advanced infrastructure can produce goods locally at lower costs, potentially eroding the traditional economic roles of developing nations in global supply chains. This technology gap introduces the risk of a severe brain drain. Skilled workers and capital may migrate toward nations holding monopolies on AGI infrastructure, concentrating wealth and innovation in already advantaged regions. Addressing these disparities will require global collaboration, including technology transfer agreements and investments in digital infrastructure to ensure AGI benefits are shared equitably. The arrival of AGI disrupts the historical link between human labor, income production, and the traditional structures of global trade. In a post-labor economy, comparative advantage shifts to uniquely human traits: emotional resonance, ethical judgment, and cultural interpretation. This transition leads to the last praxis, the stage of purposeful action where humans find relevance in an AGI-dominated world. This 5-tier framework provides a structure for human distinction. Tier 1 establishes a universal floor of basic resources. Tiers 2, 3, and 4 reward community building, cultural preservation, and leadership. Tier 5 represents legacy and transcendence, reserved for contributions redefining humanity's journey with AGI. Humanity's ultimate role involves acting as the explorers and meaning makers who guide the vast capabilities of the AGI universe. Our future depends on recognizing the distinction between statistical correlation and genuine cognition. By engineering true moral architectures and evolving our societies into legacy makers, we can secure a future defined by purpose and progress.